Okay, good afternoon, everybody. So today, I just want to give you a sneak peek of this paper that will come out soon, led by a student. So the key question that we try to tackle in this paper is to ask whether or not we can measure the eccentricity of a binary just based on a single snapshot from Gaia. So classically, this might seem impossible because of the way that we have been measuring the eccentricity is by monitoring the radial velocity. And this, of course, too expensive because for most of the stars, we would not have the time series. So the key idea of this paper that we try to promote is to use the simple fact from the Kepler's law that if you have a circular orbit, then you expect the vector v and r to be perpendicular to each other all the time. And this is not the case if you have the eccentric orbits. So what this means is that just by measuring these angles from millions and millions of stars from Gaia, you would be able to understand some of the formation of binaries. So if you with that, but do talk to me if you want more information.
We have Sarah, but Sarah couldn't make it. I think we have
me, Jeffrey.
Yeah, Jeffrey. Okay,
I'm being Sarah, then I'm going to be myself after this.
Okay.
All right. Lithium abundances in stars are really interesting and informative. Lithium is made in the Big Bang nucleosynthesis and destroyed in stars, so it's used to study a number of questions in stellar evolution and galactic archaeology. Today I'm talking about stars that have too much lithium and how GALAH can explain them. It's been known for about 40 years that 1% of giants are lithium-rich. There have been a number of proposed explanations, but for a long time we didn't know enough lithium-rich giants to study the population effectively. That has changed in recent years, and the strength that GALAH brings to this problem is a large and homogeneous set of high-resolution lithium abundances. In a paper this year, one of the new things we were able to show is that the red giant branch and the red clump stars have different occurrence rates as a function of metallicity, and it is important for understanding which processes for lithium enrichment might be at work. The other major result to come out of GALAH lithium abundance recently is by Kamara and others in 2020, who made the claim that all stars produce lithium when they move on to the red clump. This would be an aspect of stellar evolution that we hadn't noticed at all until last year, which is an exciting thought. So we're working on a follow-up paper with a model for lithium enrichment in red clump stars. So that's this for Sarah's thing.
Yeah. Next one.
Okay. So we've just been talking about lithium in giant stars. So now I'm going to talk about my own work, which has been lithium in dwarf stars. So obviously, as among the 30 elements that GALAH measures in stars is lithium. And so there's been long tension between the amount of lithium measured, the amount of lithium predicted to have formed in the Big Bang, which is the gold bar on this plot, and the amount of lithium that we measure in old dwarf stars in the halo of our galaxy, which is the points on this plot. And this difference is known as the cosmological lithium problem. So I was interested in seeing if the cosmological lithium problem is in fact cosmological, because all the stars we've been doing this for are in our galaxy, because you need to make this measurement in dwarf stars, and we can't measure dwarfs, we can't observe dwarf stars, measure the lithium in dwarf stars in other galaxies. And so I was interested to make sure that, does the lithium look the same in other galaxies? So thanks to Gaia, we now have the Gaia sausage enchiladas accretion event, or at least we've discovered it thanks to Gaia, and that gives us a large sample of stars that are born in another galaxy. And so what I did was to identify these extragalactic dwarf stars that we have observed in the GALAH survey, serendipitously, and to compare the sausage stars to the in situ Milky Way stars. And we find that there's just no difference in the lithium abundances for these two sets of stars. And this tells us that the cosmological lithium problem cannot be solved by invoking some effect of galactic chemical evolution, such as the first stars highly depleting lithium. This should be different in different mass galaxies. So yeah, you can go read the paper.
Great.
You can scan the QR code. We're all used to that now.
Thank you, Jeffrey. Okay, so then we have Sven.
Awesome. Yeah. So Jeffrey showed you that we have worked with accreted stars, but the question that you might ask is, how do we actually know that these stars are accreted? And that's something that I have worked with. So at the very beginning, Joss already showed you this interesting figure in the middle, where people have identified stars that they think are part of what is called the Gaia sausage enchilada, so like a massive accreted structure. And the interesting thing is we cannot tell them really apart based on their lithium abundance, but there's a lot of different other abundances that we can use thanks to different enrichment sources from supernovae. And I have identified some of these, as you can see on the left. Some of them are sodium, magnesium, manganese, and we can use them to identify stars all over the galaxy that are possibly accreted and part of this substructure. And then we can use this information to actually study how the dynamics of these stars work. So we know that they're on very eccentric orbits, but basically, if we have the chemistry and the dynamics combined, we can really study the chemodynamics. And the paper is in the collaboration review, so I hope it's on the archive soon.
Cool. All right. Last one from Boquan.
Yep. Can you hear me?
Yes.
Good. Hi. So I hope you're convinced from Michael and Sanjeev's talk that there is a trend of metallicity in the Milky Way with radius. So what I'm trying to do here is to create a physical model compared to Sanjeev's analytic model. So in case where you wonder what physical means, here's a flowchart of the model. So you can see we have to make assumptions on the different parameters in the model, including star formation, and also type 1a supernova delay time distribution, and also radio migration. And once we finish running the model, here's what we get. So you have a series of tracks from the galactic center that extends all the way out to the outskirts of the Milky Way at different time steps. So you can actually use these tracks to actually track the evolution of chemical trends in the Milky Way. So the paper is coming. So if you're interested, talk to me more.